I wanted to correct something. I misspoke something when I posted this lecture on photoelectrochemical effects, and I also wanted to add a clarification. So, in this slide, at around 22 minutes of the lecture, we had presented the results in the context of an N-type semiconductor. And I meant to say that a similar analysis can be done for a P-type semiconductor, but I misspoke. I said it can be done for an N-type semiconductor. So please correct that, note that. So it should be for a P-type semiconductor. So in contrast to this analysis, for a P-type semiconductor, the majority carriers are holes and the minority carriers are electrons. So in this context, the photocurrent in a p-type semiconductor is provided by the electrons. In this context, the photocurrent for an n-type semiconductor, it is provided by the minority carriers holes. However, in a p-type semiconductor, the minority carriers are electrons and they provide the photocurrent. So that must be corrected. I misspoke. I apologize for that. And the clarification which I wanted to provide is the following. So at OCV, the net current is zero. So we had derived all these things. Let's try to interpret this slightly further. So in this analysis, we are analyzing N-type semiconductor, right? So the photocurrent is due to minority hole current. At OCV, hole current should be balanced by electronic current. So that is the condition for open circuit voltage, right? So there is photocurrent, which is because of minority carrier hole current. This should be counteracted by electronic current. That is, the whole current goes from this region to the surface. There should be a counteracting electronic current uh, so that the net current becomes zero. Okay. So that is why there are two terms, and mathematically you derive this condition. The two terms, one term is because of photocurrent, the other term is because of this component. So this is the reason why the O potential eta OCV is negative. So in fact, you can make it make more sense. When you increase the photocurrent, you have to increase this component to balance the photocurrent, right? So how can you increase the photocurrent? One simple way is increase the light intensity. If you increase the light intensity, the photocurrent increases. Therefore, to have eta OCV in the new condition with increased light intensity, you have to be increasing this. So that would happen when eta becomes more negative at higher photocurrent. So you increase light intensity, this increases, eta OCV will become more negative or cathodic at higher photocurrent. That probably makes good physical qualitative sense. So it is important that while we set up the fundamental equations based on thermodynamics, kinetics, and transport, at least in this case, within the scope of this course, you should also be able to qualitatively and physically interpret what is happening, the results from the mathematical analysis. So please note these points to make sense of the sign for eta OCV. Uh, with that, let me close this particular lecture. Thank you.